and I'm still having sexy voice problems. Okay. So yesterday, a little rough. I realized it was way early in the morning, and we're like returning to the world of calculus BC. And you guys were kind of like deer in the headlights yesterday. For those of you that were awake, you were deer in the headlights. And today we are getting back into it. We are full on calculus BC mode. If you are rusty, I would recommend that you find your integration foldable and you review those integration rules. I'm just going to expect that we just picked up and left off for where I left off. It's going to feel a little weird right now, but I want to go backwards in time. I want to go backwards in time to the day of the chain rule. Chain rule for derivatives, you guys know and should know well. The key that you know that you're doing a chain rule is, I want to use fancy vocabulary here, right? You've got a function inside of another function, but the fancy word for that begins with a C. Not the chain rule, no, I didn't think about that. When you have a function inside of another function, the fancy proper math word here begins with a C. Composition. Right, you have composition of functions. At least for now. Okay. And the chain rule says when you have the composition of two functions or more functions. Hi, Lewis. Sure. I know, why not? Okay. So chain rule says we take the derivative of the outside function and we leave the inside function alone, and then we multiply by the derivative of the inside function. I'm not interested in proving this right now. You guys know this. You've seen this. Everybody mostly okay? All right, so do what you can. I want you to take 4 minutes working with the people that are around you to find as many of the derivatives in 1 through 6 as you possibly can. Only going to give you 4 minutes. Don't worry about simplifying them. Just find those derivatives. Feel free to check in with the folks around you if you need to. Is anybody else still impressed with this one? Yeah, just make a pile on my desk, I'll take care of it. Real quick, Palomar, on this first one, what's the baby, what's the mama?
The baby is 3x to the 4th minus 6, and it's 6x, and the mama is 1/2 to the x squared.
Right, it's like the square root, right? And so if I take the derivative of the square root of x, that's going to be 1 over 2 times square root of the stuff, right? So it's going to be 3x to the 4th minus 6x. Of course, we're not going to be finished there. Now we're going to go and multiply by the derivative of the baby. So we're going to have 12x cubed minus 6 parentheses. So important. So important. Everybody okay with this first one? All right, Giselle, when you look at the second one, do you see this as a composition of functions? Is there like baby and a mama? Where's the baby? Okay, so there's the baby, and what's the mama function? 2e to the x power, right? Because it has to be a function. So if we take the derivative here, what's the derivative, Giselle, of 2e to the x? It's going to be 2e to the x, but really it's going to be 2e to the baby power. So is it 5 sine of x plus 3? And then times the derivative of this guy over here, right? And the derivative of this guy over here is 5 cosine of x. And of course you could simplify if you wanted to, but that's not the point right now. Myra, number 3, when you look at this one, do you see a baby in a mom?
Yes.
Where's the baby?
The baby is e power negative t plus 8
Okay, good. There's your baby. Where's the mama?
sine.
Okay. But I want to make sure we're saying it's not just sine, it's like sine of stuff, right? It's sine of x. And so the derivative over here, Myra, what's the derivative going to be?
Cos parentheses e
Yep.
power negative t plus e to the power 2 minus negative e to the power.
There you go. Negative e to the negative t plus e to the t. And we can play this game all day long. Everybody's okay? Good. Now you might be like, why on earth are we doing this? And for those of you that of course are like 15 steps ahead of me and you want to look at 4, 5, and 6, there they are. Let me erase so you can actually properly see them. Again, not worried about simplifying, just worried about refreshing your thinking process here. Hey Lewis, nice to see ya. Okay, so you might be like, why? Why would we do anything with the chain rule? Why would we do anything with derivatives when the unit that we're in is all about integration? The reason is, you guys know, and I hope you remember, and you might just want to jot these down somewhere on the side, when I ask you to do something like this, Ale, how do you properly read this again?
The indefinite integral of x to the power 4 with respect to x.
The indefinite integral, thank you so much for catching that, indefinite integral of x to the 4th with respect to x. There's a question here that I'm asking, right? What's the question? What's the question? We've got the notation, we've got all the words that came out, but what's the question? Okay. The question is, what function do I know of that has x to the 4th as the derivative? This is the derivative, and I'm asking you, what function would I take the derivative of to get to x to the 4th? And there was a way that we would do this called the power rule. You add 1 to the power and divide by the new power. So the antiderivative of x to the 4th dx is 1/5 x to the power of 5 plus c. Plus, remember that's your constant of integration. This gives you the family of functions, because when I take the derivative of the constant's just going to be 0. All right, real quick conversations with folks next to you. I want you to find the integral of sine of x, the integral of e to the 3x, the integral of 1 over z dz, and the integral of secant of x times tangent of x with respect to x. These are all in total, take you less than 2 minutes. Thank you, Mr. Link.
Okay.
And if you need to use that integration foldable, it's okay. Integral of sine of x. The question you need to be asking yourself is, what function would you take the derivative of to get sine of x? Andrew, what do you think? What function would you take the derivative of to get to sine of x?
Negative cos
It would be negative cos.
plus c.
There might be something there that I don't like. How about negative? Give me an angle. All right, negative cosine of x plus c. Okay, Lewis, how about indefinite integral of e to the 3x dx? Or, said another way, what function would I take the derivative of to get to e to the 3x?
1/3
1/3
e to the plus c.
plus c polymon. What about the integral of 1 over z dz? What function do you know of that you take the derivative of and get 1 over z dz? You shouldn't know anything. Don't ask her. What function would you take the derivative of to get 1 over z?
1 over z would be
The natural log.
The natural log.
natural log of z.
Z.
Absolute value.
Thank you. Definitely need to have absolute value bars there. We've got some domain restrictions that we need to be careful about. Plus C and anybody. Integral of secant of x times tangent of x. David, what you got?
Secant of x.
Secant of x plus c. Is everybody mostly okay? These are the kinds of problems that we were doing before Christmas break, right? That is like forever ago. These are the kinds of problems I would expect. You're like, pop, 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 pop. I can do it all day long. I see it, I see it, I see it. It doesn't take that long. What could be hard? Well, eventually you're going to start looking at problems like on page 22 that this is really how we're going to spend the next couple of days. Look at these beautiful integration problems. Oh my goodness. These are some beautiful things. Steven's excited. I know I'm excited about this. These are not the kinds of problems that I would expect anyone in the room, myself and Mr. Link included, okay, to just look at and be like, boom, I know what the answer is. These are some ugly integrals. Really ugly integrands. These are some ugly mothers, okay? But here's the thing. If you put on your chain rule glasses, if you start to think about the fact that what is this integrand, right? The integrand, this is like all the stuff inside here. When I talked about the integrand, is there some evidence that this could be the result of a chain rule derivative? Let me say that again. Think chain rule. Think undoing chain rule. I know, there's a reason that we went over the chain rule. Now, normally when we do a chain rule, right, you guys know that the derivative of f of g of x, we just talked about this, is you take the derivative of the mama, and the baby gets left alone, and then you multiply by the derivative of the baby. Whenever you do the chain rule, there is the original baby, and there's the derivative of the baby. And it's that combination that we're going to be looking for in all these problems to be like, oh, I get it. This is the result of the chain rule. Everybody okay? Okay. Have a quick conversation with somebody near you. When you look at this first one, what do you think the answer is? What do you think the indefinite integral is? So I've heard from at least 2 people, and I've seen written down on a couple of pieces of paper that, oh, it has to be x to the 4th minus 3x squared all raised to the 6th power. How many guys would agree with this? If that's right, then take the derivative. Take the derivative, right? This is like back in like 2nd grade. You learned addition, or you learned subtraction, we checked it with addition. You learned division, we checked it with multiplication. If this is the indefinite integral, then take the derivative, and do you get back over here? You actually don't get back over here because the chain rule would say, bring that 6 down in front, 6 times all the stuff to the 5th power, times the derivative. And that's pretty good, except for the fact that I'm not multiplying by 6 over here. So the way that you can adjust for this is to just say multiply by 1 over 6. And that is the correct indefinite integral. And for some of you, I have no doubt that by the end of the day tomorrow, you're going to be looking at some of these, and just as you were able to do these pretty quickly, you're going to be able to do these problems pretty quickly. But what I want to do is I want to teach you a technique called integration by substitution. If we're lucky, we're going to get through 2 of the problems right now. And integration by substitution is really going to be a good way for you to just practice these tricky integration problems and just have faith that I'm not lying to you that this actually works. Stephen, if I'm over here, can all the friends at North Central see me?
Yeah.
Awesome. So this is called integration by substitution. I may or may not have given you enough room to to write on there. If I didn't, I apologize. You know, I'm still sick. Of course, I made the copies like a month and a half ago and I wasn't sick then.
Alright.
You think I was sick then? It was just a different kind of sick?
Yeah.
Okay. Sick and twisted.
Benefit of the doubt.
There you go. Okay, so looking at this problem, do you guys all pretty much see that there's a baby
Yeah.
and derivative of the baby? Where's the baby, Lewis?
X to the fourth minus 3x squared.
X to the fourth minus 3x squared is the baby. I'm not going to say raised to the fifth power, it's just the stuff on the inside. And the check, do I see derivative of the baby? That's this guy over here. This is baby prime. With substitution, what we're going to say is it's called U substitution. What we're going to do is we're going to rewrite this problem. We're going to say let U represent the baby. So x to the fourth minus 3x squared. So first we identify the baby. We're going to rewrite the baby as something simpler. Next, we're going to take the derivative of the baby with respect to x. So du dx, I'm taking a derivative of my baby. X is the variable, so du dx. Eileen, what's the derivative here?
4x cubed minus 6x.
4x cubed minus 6x. Everybody okay? Here comes the substitution step, and I usually try to switch colors. What I'm going to do is I'm going to rewrite my integral using these guys here instead. Stay with me. X to the fourth minus 3x squared to the fifth. Well, if u is x to the fourth minus 3x squared, then I'm just going to write this as u to the fifth. Times derivative of the baby, I have a way to write that. 4x cubed minus 6x, what is that really? du dx. Okay, and I want to be really good about my notation. I've got u to the fifth times du over dx times dx. I'm replacing the entire integrand with this substitution I do. Now, the dx that's in the denominator, the dx that's over here, those guys are going to cancel each other out. And what I need you to find now is the integral of u to the fifth du. The beauty of integration by substitution is you're taking something that was actually really ugly and really complicated in the beginning, and you're rewriting it in a more compact, simplified form where I would expect everybody in the room knows what the integral of u to the fifth du is. Or not.
Oh,
Or 1/6.
It's 1/6 u to the sixth power, because what you're doing is you're doing a power rule. You're saying, let me add 1 to the power, let me divide by the new power, and so what you get is 1/6 u to the sixth power plus c. Now, is that the final answer? Not yet. Your original integral involved x was the variable. This substitution was to kind of get it down to a more compact form. So just at the end, you're going to go back and you're going to say, oh, so this is going to be 1/6 of x to the fourth minus 3x squared to the sixth power plus Charlie. Are you kind of okay? For those of you that are gifted in the ways of just angels whisper to you, you don't have to do integration by substitution. If you're able to just look at a problem like this one or one like this one and you're like, I've got this, it's okay. Go for it. But I'm going to keep modeling this integration by substitution because the problems are going to get way crazy. And when we hit BC, there's some things that are like a double integration by substitution that no one's going to see coming. So with that said, see what you can do at number 2. I would love to. Wait, say it one more time? Oh, I thought you guys had to check your nose.
Because this would be the derivative. Yeah. 5x.
Remember, you're looking for baby, and derivative of
I think
baby.
the baby's first.
You gotta get both.
No, because wouldn't this be the girl?
Oh, which one? So not the five.
Okay, a couple of quick things. Number one, there's a lot better work.
All right, so who's got it? Now, the final answer. Where's the baby?
Oh,
David, where's the baby?
5, 5, 7.
So you're saying that that's the baby, and the thing is that could be the baby. It's possible that it's not the baby. You're gonna know for sure that it's the baby if you also see derivative of baby. Lewis, do you see the derivative of the baby somewhere?
The coastal red.
I don't agree with you. If the baby is 5 times sine of x, then the derivative of the baby is not cosine of x, it's... If this is the baby, what's the derivative of the baby?
Derivative of 5 is sine.
Well, the derivative of 5 sine of x, what I heard you say is the derivative of 5 sine of x is just cosine,
I
But-
thought-
but the derivative of 5 sine of x would be 5 times cosine of x.
Yeah.
Do we have 5 times cosine of x in this integral?
No, but I was saying that it was sine of x.
Oh, you're saying baby is just sine of x. Oh, that could work too. I'm not going to do that, but... So let's say that u is 5 sine of x. Are we okay with that? Your next step, right, for all the process people, after we identify the baby, the next
You can just do
we're going to take the derivative of the baby with respect to x. It needs to be with respect to x in this case because x is the variable. The derivative here is 5 cosine of x. So let's do the replacement here. I've got 10 e to the baby power, so that's really e to the u. A problem is this cosine of x. I want to replace cosine of x, but what I know is that the derivative is 5 times the cosine of x.
Couldn't you just like make 2e to the 5 sine of x and then make it 5 cos of x?
So what I heard you just say is, could you make this
2.
instead of 10 e to the times cosine, kind of think of rewriting it as 2 over here and move the 5 over here in multiplication?
Yeah.
That works, right? You guys are going to see this in a whole lot of different ways. Some folks are going to say, well, if this is the derivative of the baby and I've got cosine, what if I multiply both sides by 1/5? Is that legal? Right, so I'm using like proper equation stuff. Sorry, my brain's not fully working here. So 1/5 du dx is cosine of x. So now I do have a way to replace cosine. I'm going to make it 1/5 du dx times the dx. Clean it up a little bit. The dx and the dx are going to cancel out. 10 times e to the u times a fifth. Stephen's idea of like, isn't that really just 2 times stuff? It is. You're going to get 2 e to the u du. Antiderivative of 2 e to the u du. What function would I take the derivative of to get 2 e to the u? Not e to the u, you gotta be really careful. 2 times e to the u. Because that's the only way you're gonna get this 2. If you needed to, you could factor out the 2 and just say it's 2 times the integral of e to the u du, and the integral of e to the u du is e to the u plus Charlie. So 2e to the 5 sine of x plus Charlie. I've got no doubt that the 10 of you are going to see a lot of these problems in multiple different ways, and that is really good. David had 2e to the 5 sine of x plus c. You saw it right away and didn't have to do substitution. But I'm definitely going to write really hard problems, and I'm going to push you to start thinking in different ways. That having this idea of integration by substitution under your belt is going to be really good. Okay? Cool. So with that, tonight's homework is get all the multiple choice finished. And